Hello, calculus students. So here's the video for lesson 4.3, concavity and the second derivative test. Let's say this word together. Concavity. Concavity. Okay, that sounded beautiful. So I'll just read this introductory paragraph. The first derivative tells us part of the shape of a graph, namely whether the function is increasing, decreasing, or constant on an interval. This is only part of the story of the function on that interval. A good storyteller will also tell us how that function is increasing or decreasing. So let's look at these two functions below. Both of these are increasing. They're both increasing, so they both have positive slope. But as you can see, they're clearly increasing differently. And the way that they're increasing differently affects what's called the concavity. So these two graphs have different concavity because this one is increasing at an increasing rate. It starts increasing faster, and this one's increasing at a decreasing rate. It's decreasing slower. So let's look at this bold box down here. It says, if f prime tells us how the y values of a graph are changing, then the derivative of f prime, or f double prime, tells us how the slopes of f are changing. So the second derivative tells us how the slopes are changing. Let's summarize this in this box in the bottom. Okay, summarize these ideas. If we look at these two different graphs, you can see there's these little tangent lines, and remember, the tangent lines represent the slope at a given point. So we have those tangent lines, and here's the tangent lines for this one. For this graph on the left, you can see that the lines are getting steeper and steeper. So basically, we can summarize this as the rate of increase is increasing. And I'm just going to write this a few different ways. Okay, there's a few different ways we can say this. We can also say, instead of just the rate of increase, we can say the slope is increasing. This happens when f double prime, the second derivative, is greater than 0. And the word we use for this, remember we said that word concavity in the beginning? This is called concave up. Okay. Looking at this one, these tangent lines are slowly getting less steep. It's still increasing, but the rate of increase is decreasing. So the slopes are decreasing. This occurs when f double prime is less than 0. And instead of concave up, we say this is concave down. Okay. Here's kind of summary of the different types of concavity. There's just concave up or concave down. Let's flip the page. Okay. So it's a little annoying. This text box is referring to the two graphs that were on the previous page. So we already took notes about those graphs on the previous page. In example 2 right here, we're just going to draw a picture of a happy guy and an unhappy guy to help you remember those two words, those new vocabulary words, concave up and concave down. So we can say, smiley face here, this is concave up. Get it? Like a U, concave up. And then a frowny face, I like to say concave down like a frown. I think this is very helpful. Concave up, U, concave down like a frown. Very, very cute. Okay. So this picture down here, this is just going to help us practice identifying where the graph is concave up and where the graph is concave down. So we're supposed to list the open intervals. Concavity happens on open intervals, basically because where the graph changes from concave up or concave down has no concavity. So it's always on open intervals in which the graph of the function is concave up. And we're going to definitely abbreviate this to make it easier. So concave up will be CC up, and concave down will be CC down. Discuss the values of x at which the concavity of f changes. Okay. So let's first think, where is this concave up? So let's look for all the smiley faces. Scan through there for the smiley faces. Definitely see some. Here, I'll do them in yellow. Here's a smiley face. Here's a smiley face. Here's a smiley, part of a smiley face. So those are all my concave up intervals. So that goes from B to C in union with, so this kind of means and, D to E. Remember, I have to split these two up into different intervals because at this point right here, it's neither. So the points where it kind of changes like that, I'm going to need to split it up. So here's one interval, here's the other interval. We can't include the point E because that's a point where it's sort of changing. Okay. And then concave down, I can do my frowns in this lighter green. Here's a frown, here's a frown, here's a frown. So that goes from A to B in union with C to D, in union with P to Q. Woohoo! And then it says discuss the values of x at which the concavity of f changes. So basically, maybe I'll put them in black. The concavity changes when I change color. So when I change from a frown to a smile or a smile to a frown. So it changes at these points. Not here. It's still concave up there, so here. So I'll say concavity changes at x equals B, C, D, and P. Not too bad, huh? Now I'll say those dreaded words. Turn the page. Let's see what's next. Ah, some theorems, some rules. Okay, so up here it says, we would like to be able to find the values of x at which a function can change its concavity from the equation. So we were just looking at it graphically. Now let's check out the equation. Using similar methods to what we did in 5.3, once we find these values, called PIVs, this stands for possible inflection values, we can test the intervals in between these values to determine the function's intervals of concavity and its actual inflection values. So what this is referring to is when we made those line charts to determine where the maximums and minimums were by looking to see where the graph was increasing or decreasing. We're going to do the same thing here, except we're going to be looking at the concavity. And if we're looking at the concavity, that means instead of observing the behavior at the first derivative, we're going to be observing the behavior at the second derivative. Okay. So, in order to test this out, to find the concavity, here are our steps. 1, we'll find any discontinuities of a function of f of x. 2, identify any potential inflection values in the domain of f of x by finding where f double prime equals 0 or f double prime does not exist. This is very, very similar to the first derivative test that we used to find maximum and minimum values. For the first derivative test, when f prime equals 0 or f primes do not exist, we had critical points. But when we're looking at f double prime, where it equals 0 or does not exist, we're looking for potential inflection values. So just a little bit different vocabulary. Inflection values is where concavity changes. 3. Using a number line chart, we'll test the intervals by finding the sign of f double prime on all the intervals between any potential inflection values and discontinuities. On the intervals where f double prime is greater than 0, f of x is concave up, like a cup, or like a smiley face, on that interval, and on the intervals where f double prime is less than 0, f of x is concave down, like a frown, on that interval. Okay? The number line will also help us determine where there's an inflection point. So here's just definition for an inflection point. Basically, there's an inflection point when the graph of f changes from concave up to concave down, or vice versa. So if it changes from concave up to concave down, or concave down to concave up, then there's going to be what's called an inflection point there. Okay. I know there's lots of text at this point. We'll get to some lovely examples in a second. So finally, these are just some of the summary points about concavity and points of inflection. It's repeating a lot of what has already been said, but it bears repeating. So concavity can change at a discontinuity. Remember, a discontinuity is where f of x does not exist, such as a vertical asymptote, but it won't be an inflection point. Okay, so concavity can change, but that does not mean it's an inflection point. To find the possible inflection points, you look to see where f double prime equals 0 or f double prime is undefined, does not exist. Not every possible inflection value is an inflection value. Remember, you need to change signs of f double prime. So f double prime has to change signs either from positive to negative or negative to positive for it to be an inflection value. Okay. And then this just says, a chart can help you efficiently test for concavity in between possible inflection values and discontinuity. So we're going to be making those lovely charts again. Example 4, let's just get to our examples. That's what I really want to do. So it says, determine the open intervals on which the graphs of the following functions are concave up or concave down, then find any inflection points. Justify. Oops, got a text. Anyway, so the first thing we're going to do is let's solve for f double prime. So y prime equals 3 goes away. The derivative of sine is cosine of x. So y double prime, the derivative of cosine is negative sine of x. So remember, we want to find where f double prime equals 0 or f double prime does not exist. There's nowhere where f double prime does not exist because that trig functions are always continuous. I need to silence my phone, sorry. keeps going off. There we go. Stop texting me. So let's figure out where this equals 0. Think back to your unit circle. Where does sine of x equals 0? Sine of x will equal 0 where x is, and remember we're just between 0 and 2 pi. At 0, at pi, and at 2 pi. Okay, so these are my possible inflection values. They're just possible. We have to test to see if they are actually inflection values. So we'll make our chart. 0, pi, ooh, what am I doing? Pi and 2 pi. Zero pi, 2 pi. And we actually don't have to go to these sides because my interval just goes from 0 to 2 pi. So I just need to test here and here. So let's imagine we had pi over 2. At pi over 2, we plug it into y double prime. If you plug pi over 2 into negative sign, you would get -1. So that's a negative value. And if you plug 3 pi over 2 into negative sign, you would get +1. So that's positive. So to summarize this up, we're looking to see where it's concave up or concave down and any inflection points. So this is concave up from pi to 2 pi. Concave down from 0 to pi. And then the inflection point is at x equals pi, because that's where the concavity changes signs. It's where y double prime changes signs. Not too bad, huh? I don't think so. Okay, let's look at this example. This thing is continuous everywhere. So let's look at the second derivative, so f prime of x. And that will equal, we can just do the power rule here. So bring down that -1, we get -6 times x squared plus 3, subtract 1, that becomes -2. Chain rule times 2x. So to simplify a little, f prime equals -12x times x squared plus 3 to the -2. It's a slightly more labor-intensive second derivative. Ugh, to be honest, I don't love it personally, but we can do it. The reason why it's a little bit more labor-intensive is because now I have two functions. So I have to use the product rule. So I'll start the product rule by taking the derivative of the first one, which will be -12. The second function stays the same. And then now I'll have the first function stay the same, so -12x. Take the derivative of the second one, that will be times, bring down the -2, times -2, x squared plus 3 to the -3. Chain rule times 2x. Oh no. I don't know if I'll be able to do that problem. I went too far. That's okay. Let's simplify this a little bit. So this is -12. I'm actually going to bring this down. So -12 over x squared plus 3 squared. We've got two negatives, so this will turn into plus 12 times 2 times 2 is 48x squared. So I have x times x. And then I'll bring this binomial down, so that's x squared plus 3 to the third power. Sorry, I was looking at my notes for a second. I got distracted. So, I want to find where this thing equals 0. Right? So, I'm going to combine, basically this thing is going to equal where the numerator is equal to 0. So, I'm going to combine these fractions. It's not too bad. I just want a common denominator, so I'm going to multiply this fraction times x squared plus 3 on the bottom. And if you do it to the bottom, you got to do it to the top. X squared plus 3. So then I'm going to have negative 12 times x squared plus 3 plus 48x squared all over x squared plus 3 cubed. So now I just have one fraction. Set that equal to 0. So this is going to equal 0 when the numerator equals 0. So I can honestly kind of just forget about what I have down here. So I have negative 12x squared minus 36 plus 48x squared equals 0. I want to find where this equals 0. Because I'm looking, just to note, where f double prime equals 0. So if the numerator equals 0, then the whole function equals 0. So this is negative 36x squared minus 36 equals 0. Factor out negative 36, you get x squared plus, oh no, this shouldn't be negative. That's positive, so this is positive as well. So then I get x squared minus 1 equals 0. So the x values are plus or minus 1. Okay, so this is where f double prime equals 0. And we also do, this comes from the numerator, we also can look to see f double prime is not going to exist. F double prime does not exist when the denominator equals 0, so we can set that thing equal to 0. I want my black. So if I set x squared plus 3 cubed equal to 0. If I try to solve this out, I could basically say when x squared plus 3 equals 0, or when x squared equals negative 3, there's no values here. So no x values. I just wanted to check it. Okay, so there's no x values I could plug in where x squared equals negative 3. So this kind of didn't lead anywhere. I just wanted to check. So these are my possible inflection values. You're all probably like, Miss, this is so extra. This is so much extra work. But yeah, kind of was a little complicated, I'll be honest. So these are my possible inflection values. This was the hard part. Now I just make my little chart looking at, yeah, we're totally just not even going to do this. I'm running out of space. So looking at f double prime, and we have the values negative 1 and positive 1. So if we plug these into f double prime, I'm not going to make you do this. I'll just, spoiler, I'll tell you. So if I plug in like negative 2, we would get a positive value. If I plug in 0, you would get a negative value. And if you plug in 2, you would get a positive value. And actually a shortcut for this would just be to plug it into this equation here, because you know the denominator is always going to be positive. So you could just plug it into the numerator. That wouldn't be too bad. Okay, so here's my chart for concavity. Again, this is the nice easy part. So this is going to be concave up on these two intervals. So it's concave up from negative infinity to negative 1 in union with 1 to infinity. It's concave down right here from negative 1 to 1. And so these were possible inflection values, but after doing this chart, because the concavity changes at both these points, now I actually know these are indeed inflection points. So inflection points at x equals negative 1 and x equals 1. Woo! Go calculus students. I don't know why they give us such a tiny spot for that. Okay. So on the back, there's a bunch more problems. Oops. Where it's just practicing the same things. So finding where the concavity changes and the points of inflection. I'm just gonna do one of these. Which one should I do? I will do I'll do this one because the notes I took for it on my other page are really messy. So hopefully I can do this slightly more neat. I'll do this one with the piecewise function. The piecewise function I think looks more intimidating than it is. We still want to start just by finding the second derivative. I think for me personally, it's going to be easier if I just rewrite this. So this first one is going to be negative x to the 1/2 for x less than or equal to 0, and then I can just leave this as x squared for x greater than 0. This is a continuous function. If we plugged in the point 0, that's the only place where the discontinuity could be. If we plug in 0, they both equal 0, so this is a continuous function. I don't have to worry about a discontinuity here. So let's just find y prime. Y prime, just take the derivative of both of these. That will be 1/2 negative x to the negative 1/2 times negative 1. Don't forget the chain rule, so I'll just add a negative sign right there. For x is less than or equal to 0. And then the derivative of x squared is 2x for x is greater than 0. Okay. So the second derivative, the derivative of this, bring down this negative 1/2, you get positive 1/4 times negative x, subtract 1, that would be negative 3/2, and then the chain rule, because the derivative on the inside, the derivative of negative x is negative 1, so again I'm just going to add a little negative sign there. For x is less than or equal to 0. The derivative of 2x is 2. For x greater than 0. Okay. So we want to figure out where this derivative might equal 0. This second part, obviously that's never going to equal 0, and that's never going to not exist. So we really just need to look at the first part of this piecewise function. For this piecewise function, there's no value of x that would make this 0. However, y double prime does not exist when x equals 0. So if I plugged in 0 here, since this is a negative exponent, you would have 0 in the denominator, which would make y double prime not exist. Okay, so we have a point of discontinuity for y double prime at x equals 0. So that is, so x equals 0 is a possible inflection value. That's a PIV that we need to test out. So we'll make our little chart, and we'll look at y double prime for values of x less than 0. So if we had a negative, let's say if we had -1, we would have to plug it into the top function. If I plug in -1, that would become +1. +1 to the -3/2 is still just +1, times -1/4 is a negative number. Use a calculator. Go ahead, use a calculator, check my work. And then if I plug in 3, x equals 3, 3 is greater than 0, so I use the bottom function. It's always 2, so that's positive. My little sign chart is done. Now I can talk about the concavity. This thing will be concave up from 0 to infinity, and concave down from -infinity to 0. Since the sign changes right there, you do have a point of inflection at x equals 0. Okay. You should test yourself for D, E, F, and G. Go ahead, choose one to try. Choose just one to try on your own. Go ahead, pause me. Hit pause. Try one out. Okay, welcome back. Hopefully you tried that out. Here's my work for those first few. Let me do this. I know it's a little bit messy. Miss Patterson apologizes, but go ahead, pause, copy whichever ones you want to copy down. It's all the same process that we were just doing, looking for where they're concave up, concave down, or inflection point. I'm going to move this in 5 seconds, so pause me if you need to. Okay, this last example, example 5, that I want to look at, I kind of already started this problem, but then I was like, I should probably show them what this looks like. So basically, in example 5, it tells you to sketch a possible graph of a function f that satisfies the following conditions, and then it gives you a bunch of information about it. It tells you that f prime of x is greater than 0 on this interval, and then f prime of x is less than 0 on this interval. So remember that f prime is going to tell you about what's happening with the slope. So this is like a positive slope. Slope is positive when f prime is greater than 0, and the slope is negative there. So I wrote here, to help me out, I wrote it's increasing. It goes from increasing to decreasing at x equals 1. So at x equals 1 here, it's going to change from increasing to decreasing. The second piece of information it gives me is that f double prime is greater than 0, which means it's concave up on this interval, or on these two intervals, and then it's concave down because f double prime is less than 0 on -2 to 2. So we'll have some smiley faces on these intervals, concave up, and then concave down on that interval. And then it also gives me this information about the limit as x goes to negative infinity and the limit as x goes to positive infinity. This is telling me what the end behavior is. So at the end I'll just be able to draw arrows. So this tells me that as x goes to negative infinity, so as we're going that way, the y value equals -2. So I kind of already drew in this little asymptote here at -2 because I know that's my end behavior there. And then as x goes to positive infinity, the y value goes to 0. So I already drew a little asymptote there. As you can tell, these are notes actually from last year, so I don't really know what these like pencil markings are. I erased them because they look awful. But let's try to sketch this thing. So it's increasing to decreasing at x equals 1. So I'm going to be increasing all the way to here and then decreasing. I'm concave up between negative infinity and -2, so right here. Concave up, and then I'll move from to concave down until -2 to +2, and then concave up again from 2 to infinity. Okay, so here's my best attempt at this. So concave up, increasing to -2, and then at -2, I'm still increasing, but I'm going to go concave down, and then when I get to x equals 1, I'm going to start decreasing, because I decrease at -1. I'm still concave down until 2, which is when I start going concave up again. So I'm concave down, and then I'm going to change to concave up. So here and here are my points of inflection. This is inflection point, inflection point, and then here, since I go from increasing to decreasing slope, this is my critical value. I have a max right there. Yeah, that looks pretty good, I think. Much better than these pencils. That's all I'm going to show you for today, for these notes. Please make sure you get your practice on and check out these if you need to. Just remember, second derivative tells you about that concavity, whether it's concave up, concave down, what's happening with the slope. Anyway, it's late. I'm going to go to bed. Good night.